So let's look at one more example. So for the circuit shown below, we're told that our initial inductor current is -1 amp, our initial capacitor voltage is 5 volts, and we want to find the capacitor voltage equation Vc of t for our time greater than 0. So as we've seen before, our first step is going to be to transform our circuit to the S domain. So transform our circuit to the S domain. And so we're going to consider each of our components. So for our resistor, we're going to have no change. So no change in R value. And so you notice this is kind of a weird value, 10/3. And that's just because this is a textbook example. So they've picked nice numbers so everything works out nice and easy in the end. Of course, that's not always going to be the case in real examples, but it's nice when we're just getting the hang of this. So for our source, we're explicitly given this U of t as opposed to having a switch drawn in the circuit. And so taking the Laplace transform of that, we get 10/s, and so that's volts in both cases. For our inductor, we have a 5 Henry inductor, so the impedance is going to be S times L, or 5s. And because we have an initial current of 1 amp, we're going to have a source combined with this. So we're going to have either a -5 volts in series, or we're going to have a -1/s amps in parallel. So similar option for our capacitor. So we have a 0.1 farad capacitor. Our impedance of that is going to be 1/SC, or 10/S. And because we have an initial condition of voltage on that capacitor at t equals 0, we're going to have a source with this as well. And we can choose between a 5/S voltage source, which is going to be in series, or we can choose to have a 0.5 amp current source in parallel. And so what we notice is because we have an inductor and a capacitor which both have initial conditions, we have 4 possible circuit configurations to choose from. So 4 possible configurations. And again, there's not going to be one right configuration. One configuration might be easier than others, but if you're more comfortable with a certain method and choosing certain configurations here make that method easier, then by all means do that. So probably the easiest thing to do would be to look at using node voltage method. So if we did node voltage method, we could choose the options with our current sources. So if we choose our current sources in parallel, we can see again we would just need one node voltage equation. But we've looked at node voltage method in several of our examples. So let's instead plan to do this circuit to analyze the circuit with mesh current. And so with mesh current, we want to limit the number of meshes we have. So what we can do is we can choose the option to just have our voltage sources in series. So with our voltage sources in series, we're just going to have the 2 meshes, and that's going to sort of minimize our equations. But again, there's various options that we can choose. And as always, when we're inserting either these voltage or current sources, we want to be careful about the polarities of our voltages and the current directions for our current sources. Okay, so let's choose those highlighted options, and with the idea that we're going to do mesh current. So our voltage source is going to be 10/S. Our resistor has no change, so it's going to be 10/3 ohms. Now our inductor is going to become an inductor in series with the voltage source. And looking at our notes, we can see that that's going to have a negative polarity at the top. Our capacitor, likewise, we're going to substitute with a capacitor in series with a voltage source. And looking at our notes, we see that this voltage polarity should be such that the positive side is on the top. So we get something that looks like this. So now our capacitor impedance, we said, was 10/S. And the value of this voltage source in series is going to be 5 divided by S volts. For our inductor, we had an impedance of 5 times S, and the value of this voltage source was negative 5 volts. Okay, so let's keep in mind, because we're looking at voltage across the capacitor, so that's what we're ultimately trying to find as VC of t, we are interested in the voltage across both of these elements here. Because remember, this 5 over S volt source is just representing the initial conditions on our capacitor, but it's still part of our capacitor. So this is going to be our VC of S that we're ultimately interested in. Okay, so if we're going to do mesh analysis, so let's say we want to do our mesh current method, we have 2 meshes, which means we're going to need 2 equations. So the first thing we want to do is define our mesh currents. So I can come up here and I can define my mesh current I1 going clockwise in this left mesh, and my mesh current I2 going clockwise in this right mesh. And so there's not necessarily a right or wrong way to define these. We can define them going clockwise or counterclockwise. Either way will give you the same answer, so long as you're careful with your passive sign convention and your KVL as you're writing your mesh equations. Okay, so let's start with our mesh 1 then. So our mesh 1 equation. So if we start, again, we can start at any point, go any direction, but let's say we start in the bottom left and move in a clockwise direction. What we're going to have is a negative 10 over S, but let's go ahead and move that to the other side and just say 10 over S is equal to, continuing around our loop, we then have a voltage of 10/3 times I1, plus, now for our inductor, we have this impedance of 5S, but it's not being multiplied by just I1. We also have current I2, so we have to consider both I1 and I2. I'm going to put I1 minus I2 because our I1 is going down and our I2 is going in the opposite direction. And so because we're in mesh 1, we can assume that our I1 is going to be positive. The final value we have is this voltage source here. We see the negative side first, so it's going to be negative, but the value is negative 5, so we get something that looks like that. Okay, so now we're back where we started, so we finished our loop. So what we can do is we can collect terms on the left that don't have I1 or I2, and so that ends up being our 10 over S and our minus 5, and that's going to be equal to, collecting terms over here, we have I1 times 10 over 3 plus 5S, and then we have I2, which is being multiplied by a negative 5S. And so we could take this a step further. If we're going to solve by hand, we can combine these terms on the left. So we have negative 5S plus 10 over S. And that's going to be equal to our I1, combining the terms here, common denominator of 3. We have 10 plus 15S plus our I2 times negative 5S. And so to be consistent with our notes, let's call this equation 1. All right, so on to mesh 2. So I'll scroll up here, we can take a look. And again, with mesh 2, we could start at any point and go in any direction. Let's, for instance, again, just say we're starting in the bottom left and going in a clockwise direction. So the first thing we see is that voltage source, and we see the positive side first, so it's going to be positive of whatever value. And so that's going to be, so let me just start by saying 0 is equal, because we know we're going to do a full loop. So the value is negative 5. So the next component we see is that inductor, which has impedance of 5S. But remember, it has I2 and I1 both going through it. So we have plus 5S. And now because we're in mesh 2, we can say I2 minus I1. The next component we see is that capacitor, which is just going to be I2 times 10 over S. So plus 10 over S times I2. And then finally, our voltage source of 5 over S, we see the positive side first, so it's just going to be plus 5 over s. So again, we can collect terms on the left side that do not have any I1 or I2 terms, so that's going to be a minus 5 over s plus 5, and then collecting terms on the right side, we have I1 times negative 5s plus I2 times 5s plus 10 over s. Again, if we're going to solve this by hand, we can collect these terms. We can say we have a 5s minus 5 divided by s on the left, and that's equal to I1 times negative 5s plus I2, and then if we want to find a common denominator here of s, we have 5s squared plus 10. So again, to be consistent with the notes, let's call this equation 2. And so I'm going to put a couple videos up that show how to go through and solve these two equations using Cramer's method. But basically, because we don't have numbers like we saw earlier with our systems of equations for node voltage method and mesh current analysis, we can't necessarily just plug this into our matrix method in a standard calculator. Some more advanced calculators and software can do that, and so I'm going to have another video showing that. But for the moment, let's just sort of skip past that step and say we've solved for I1 and I2, and so let me write our results here. So our I1 ends up being, so in our numerator we have 1.5 s squared minus 3s plus 6. In our denominator we have s times s plus 2 times s plus 1. And for our I2, we find that I2 is equal to, in the denominator we have s plus 2 times the quantity s plus 1, and in the numerator we have 2.5s minus 1. So these are the answers for our I1 and I2 from solving equations 1 and 2. But let's go back to our problem statement. So we're looking for VC of t. So what that means is we're going to find this VC of s, and then we're going to inverse Laplace transform that. So from this circuit here, we can see that this VC of s, let's just call it V sub c for now, is equal to this current I2 times this 10 over s plus this 5 over s. So we also have to include that voltage source, which again is accounting for our initial conditions. So writing that down here, we can say that our VC of s is equal to that 10 over s, which is our impedance associated with the capacitor, times I2, plus our 5 over s, which again is related to our initial conditions. So plugging in sort of this solution here for our I2, we can say that our VC of s is equal to, we have 25s minus 10 divided by s times s plus 2 times s plus 1, and then plus a 5 over s. So what we're going to do now is just partial fraction expansion to be able to inverse transform this. So we have 3 poles in that initial function here. So we have k1 over s plus k2 over s plus 2 plus k3 over s plus 1. And then our 5 over s, of course, we already know the value of that, so we can already inverse transform that part. So using our residue method, we know we have real distinct poles. So we can say K1 is going to be equal to 25s minus 10 divided by s plus 2 times s plus 1 evaluated at s equals 0. If we plug s equals 0 in, we get 25 times 0 minus 10. So we'll have negative 10 over 2 times 1. And we get that K1 is negative 5. Similar thing for K2, we have 25s minus 10 divided by s times s plus 1, evaluated at s equals -2. Plugging that in, we get -60 divided by -2 times -1, which gives us -30. And then finally for our K3, we evaluate that from 25s minus 10 divided by s times s plus 2, evaluated at s equals -1, which is -35 divided by -1 times 1, so that is 35. So now that we know all of our coefficients up here, we can plug in and we see our VC of s is equal to -5, so let me scroll up a little bit, we had -5 for K1 divided by s, plus -30 divided by s plus 2, plus 35 divided by s plus 1, and then remember we also had this plus 5 over s term. And so in this case, what we can see is that this -5 over s will cancel out with this 5 over s. That's not necessarily always going to be the case, but in this case we do have that initial condition term canceling out. And so we can take the inverse Laplace transform of this now using our table with our properties and our known pairs, and we can find that our VC of t is equal to, so we have -30 times e to the minus 2t plus 35 times e to the minus t, so we're using our frequency shift property, and then both of those are multiplied by u of t, and our units are in volts. And so this would be our final answer for our VC of t. So one thing to note is that, of course, as I mentioned earlier, it'd be a lot easier to solve this problem if we used our node voltage method because we just have one equation. And so if you look on page 720 in the textbook, you can see what that analysis looks like. And so as I mentioned in some other videos, we'll come back and I'll talk about how we can solve these equations 1 and 2, both by hand as well as using MATLAB.